Hi, in this video we will show you the graphical representation of the Laplace transform result. This is the formula for the Laplace transform, where if you want to transform the ft into capital Fx, then you should use the Laplace transform equation like this. So in this case, your s is equal to decay or growth rate, which is written in the sigma symbol plus I omega. The exponential term here plays important analysis in the Laplace transform. So you can see that the first exponential term is to extract the transient behavior, which is the sigma, and the second exponential term is to extract the steady state behavior, which is the frequency. First of all, let's think what is the graphical representation for the exponential negative sigma t. How about exponential negative I omega t? How can we plot this? Then, how should we plot exponential negative xt? And lastly, for various ft, what should be the plot for the fx? In this video, you will learn how to plot the Laplace transform result. Please be aware that plotting the result of the Laplace transform will not be examined in this study. However, learning how to plot the Laplace transform result will be very useful in enhancing your understanding and intuitive about it. Let's plot the graph for the exponential negative sigma t. Let's say the sigma is equal to positive. So if we substitute, you should get the first case. And if your sigma is equal to negative, then you will get the second case. You can see that if the magnitude of the sigma is higher, it will decay to the zero faster. For the second case, if the sigma is higher, then the faster growth rate it will be. Let's discuss the graphical representation of the exponential negative I omega t. So we know from the Euler formula, the exponential I omega t equal to cos omega t plus the I sin omega t. So in this case, the angle is equal to omega t. So if we substitute into the equation, we can obtain the equation 1. Let's have a real and imaginary part here, and then this is our exponential I angle, which is in the real part it will be cos angle, while in the imaginary part it will be I sin angle. So this represents our first equation. By using the Euler formula, we can obtain exponential negative I angle equal to cos negative angle plus I sin negative angle. So cos angle is the same with cos negative angle, while the negative sine angle is equal to sine negative angle. So with that, if we plot it, we will obtain the E power of negative I angle to be this form, where this is the cos angle, while here is the negative I sine angle. By using the similar method, we can obtain the negative exponential negative I angle to be negative cos angle plus I sin angle. So for this position, you have the negative cos angle plus the I sin angle. By taking the first equation and the second equation here and divided it by 2. So in this case, you will find that cos angle will be equal to this. And also if you take the first equation here and the third equation and divided by 2, it will be equal to I sin angle. So if you divide it by 2i, you will get this answer. So these are the additional Euler formula that you should know. So if we want to plot the cos angle, so this is the graph, and then if we want to plot the sine angle, we have this. How about if we want to plot cos angle plus I sin angle, which is the exponential I angle based on the Euler formula? In fact, you will obtain unit cycle graph like this for the exponential I angle, where you have the cos angle at the real part and the sine angle at the imaginary part. Let's start with the first point at 0 degree. So you can see cos 0 is 1, sin 0 is 0. So you can have the rectangular coordinate like this, and then for the polar coordinate we can have this form plus I0. Therefore you have the point to be at here. How about 135 degree? So cos 135 here give you negative 0.71, and sine 135 here give you 0.71. So therefore you obtain this rectangular coordinate, and if you plot it, so this is your negative 0.71 going up by 0.71 in I imaginary. Try to practice to find the exponential I 225 degree, which is located in this point. Try to prove that. Angle is equal to omega t, where the omega is the angular velocity. Let's assume it to be 360 degrees per second, or is a 2 pi radian per second. So with that, we can plot the cos of omega t, where you can see you have one cycle in 1 second. Same to the sine omega t, where you also have one cycle in 1 second. So try to think, how can we plot the exponential I omega t, or cos omega t plus I sine omega t? How can we plot this? Let's have the axis cos angle, imaginary I sine angle, and also the third axis time. So previously, when we consider only the angle, you obtain a unit cycle because we only consider angle. So you have a 2D plane. But in this case, we have omega t, so it will be a 3D. So at time equal to 0, you obtain the point to be here. So you can check at t equal to 0, your cos 0 is 1. So the real part is 1. And then when t equal to 0, your sine 0 is equal to 0. So this is the position. So as time goes, let's say at t equal to 0.375, so let your t to be 0.375, you obtain this point, and it's around negative 0.7. And then substitute t equal to 0.375 into the sine function, then you obtain here, which is around 0.71. Okay. So if you plot it, so the real part is negative moving backward, positive moving forward. So moving to here by negative 0.7, and then 0.71 in imaginary part. So since it's a positive, it will go up by 0.71. So this is the point. So if you plot it, you obtain the point to be here. Then at t equal to 0.625, using the same method, you obtain the point to be here. So you can see that the point is rotating counterclockwise with respect to the time axis. So this is the graph for the exponential I omega t, where you have the cos omega t axis, I sine omega t axis, as well as the time axis here. At time equal to 0, you obtain the point to be here. At time equal to 0.375, you obtain the point to be here. At time equal to 0.5, you obtain the point to be here. Time equal to 0.625, you obtain the point to be here. Then at time equal to 1, you obtain the point at here. Since we assume that our omega equal to 360 degrees per second, so that means this curve will rotate for one cycle for 1 second. So you can see that if you have more time, you have more cycle. So for this, you have 5 seconds, you should expect 5 cycle because your omega equal to 2 pi. So you start from t equal to 0 here, and you rotate in the counterclockwise, right? So 1 cycle, 2, 3, 4, and lastly 5, and it go back to the original position. So you can see the animation for this graph here. So as time goes, it rotates counterclockwise forward. The graph for the exponential negative I omega t is similar to the exponential I omega t. So the difference is on the direction for the rotation, where you can see is rotate clockwise forward. We have learned how to plot the exponential I omega t in this way, which is the isometric view. If you look from the top, you will find this view. This is the top view, where you have the real part, okay, cos omega t versus the time. If you look from the front, which is here, you see the I sin omega t versus the time. So this is the front view. Try to imagine what it will be like when you look from the right. In this view, you will have the imaginary part versus the real part. We have the name for it is called the complex plane, or is the S-plane. So this is very bottom view in Laplace transform. So for the exponential I omega t, you will see a unit cycle rotate in counterclockwise. So if your omega is positive or negative, so if you plot the exponential negative I omega t, you will find that the direction is different, like this, which is clockwise. So if you have an object rotate in 5 radian per second compared to negative 5 radian per second, you should know that for this negative frequency, it's just the opposite direction for the rotation. So one is clockwise, another one is counterclockwise. So this is the graph for the exponential negative xt, which is equal to exponential negative sigma t multiplied with exponential negative I omega t. This is the 3D view, and this is the 2D view for the exponential negative xt. And this is the result when you take the decay function multiply with the exponential negative I omega t function. Since you have the 0 at the end of the decay function, so 0 multiply the exponential I omega t, so in the end here you should expect 0 as well. So you rotate, and then in the end it becomes 0 like this. So with that you obtain this kind of function. So if you increase the decay rate, where you increase from 0.1 to 0.8, then you see the thing decay to 0 faster. So it reach to 0 fast, take shorter time compared to the previous case. So we can say the amplitude can decrease faster to 0 if your decay rate is increased. On the other hand, if your exponential is positive, then the signal will grow. If you increase the sigma from 0.1 to 0.8, you see the magnitude increase from 20 to the 4 multiplied 10 to the power of 10. So it's so that the amplitude will increase significantly if the growth rate is increased. How if we increase the omega? What is the effect? So if we increase the omega from 5 to 10, you can see that there is more oscillation per second. This is the Laplace transform table, which you can use as appendix to convert from the time domain. Let's say you have a constant ft equal to 1, and you can convert to the Laplace domain, where you get fx equal to 1 over x. You can also use this table to convert the function like delta, polynomial, exponential, sine, cos, and etc. In this example, we will look at the ft equal to 1. So you have a constant 1. And then when you take the Laplace transform, you get the fx equal to 1 over x. And we know that s is equal to sigma plus I omega. Then you can multiply with the complex conjugate to get this answer, and expand it according to the real part and imaginary part. So with that, you obtain the real part for the fx to be this formula, and the imaginary part for the fx is this. So from this equation, you should aware that fx in fact is not a real number, it's a complex number. So complex number, like you learned previously, let's say you have a plus bi. So in this case, your real part, assume it to be A, imaginary part, assume it to be BI. And you can find the magnitude by using the square root of A squared plus B squared, where your A substitute the real part inside here and imaginary part here. Then you can find the magnitude for the fx. To find the phase, then you can take the inversion of tangent and take the imaginary part, which is B, divided by A. So your B, okay, just substitute at the top, and your A substitute at bottom. And you see the denominator can be cancelled, and in simple you get negative omega over sigma. So this is how you obtain the phase. And be careful, once you compute, you have to consider the quadrant to get the actual phase. So we can present the fx equal to 1 over x by using many methods. So first method is called the co-quad plot, which consists of real part and imaginary part. So this is the real part and imaginary part for the fx equal to 1 over x. So from here, you have the variable sigma and omega. So you should substitute your sigma from negative infinity to infinity to this equation, as well as you substitute the variable omega from negative infinity to infinity to here to form the real part. For example, at this point, your omega is 0, your sigma is 0. At this point, your sigma is negative and omega is 0. So if let's say you choose the sigma equal to 1, omega equal to 2, for example. So let's say sigma is here, this is 1, so omega is 2 is here. So this is the point. So let's say you substitute inside. Then you get the answer to be 1 over 5 for the real part. So if you plot the real part here, you should expect the height for this point at 1, 2. The height will be 1 over 5. So if you substitute the sigma 1 to the imaginary part and omega equal to 2 into this formula, you should get negative 2 over 5. So in the imaginary plot, at the point sigma 1 omega equal to 2, then you should expect the height is negative 2 over 5. So you can continue for the various sigma and various omega for the real part and imaginary part. So this is called the co-quad plot. We can also present it in magnitude and phase, which is called the Bode plot. So this is the magnitude for the fx equal to 1 over x, and this is the phase equation. So we can substitute the sigma from negative infinity to infinity, while the omega from negative infinity to infinity. So let's say at a particular point here, same like previous case, let's say it's a 1 and 2 here. So what is the magnitude? So if let's say sigma 1, omega equal to 2, when you substitute inside this formula, then you should get your magnitude equal to 0.75. So with that, you should expect at this point, your magnitude is 0.75 here. So you can compute the phase and you get negative 26.6. And based on the real part is equal to 2, imaginary part is negative 1, we know that it's fourth quadrant. And your actual angle should be equal to 333.4 degrees. So with that, we know that at this point, where your sigma equal to 1, omega equal to 2, so your phase around 333. So if you continue to find the point for all the S-plane here, Then you can form the magnitude plot like this, and also the phase plot like this. So you see that in the phase plot you have negative value. Let's say you have the phase equal to negative 20 degree. In fact, negative 20 degree is just same with the 340 degree. Lastly, we can present the fx, which is the Laplace transform result, by using the pole zero plot. So pole zero plot will use the x-plane, which is the I omega versus the sigma. First of all, you have to compute what is the pole for 1 over x. So when your x equal to 0, so you get 0 at the bottom. So this is your pole. And you found no x can make it 0 at the top. So with that, you don't have any 0. So you know the x is equal to sigma plus I omega. So when you compare to the pole value at 0 here, so 0 will be equal to sigma, and you have nothing at I component here. So with that, your omega is 0. So pole tell the characteristic of ft. So in this case, your ft is a constant. So for a constant, it's not decaying or it's not growth. Therefore, the characteristic of constant it should have sigma equal to 0. And for constant, it's not oscillating like this. So your omega is equal to 0. So pole is very useful for the engineering application. It can tell you what is the characteristic of the ft. So this is the pole zero plot. So you have I omega versus the sigma. So you draw a cross indicating the pole at I omega equal to 0 and sigma equal to 0 here. If you compare the magnitude plot versus the pole zero plot, you found that the pole zero plot is just the top view of the magnitude plot. And the pole here is indicating at the peak of the magnitude plot. In summary, pole zero plot is most commonly used to represent the Laplace transform result due to its simplicity. So we always use this instead of the other plot. Let's try with more example. So for ft equal to cos omega t, from this table we can convert to the Laplace transform fx equal to x over x squared plus omega squared. So if your ft equal to cos 5t, so your omega is 5. So I can just replace the omega to be 5. So this is your fx result. So you can easily find the pole. Okay, what make it 0 at the bottom? So x squared plus 5 squared equal to 0. You can compute your x to be 5i and negative 5i. And to get the 0, okay, what makes 0 at the top? Okay, when your x equal to 0, you will get 0 at the top. So this is your 0. From the pole, you can find the characteristic for the ft, where you can compare x equal to sigma plus I omega equal to 5i. So then you will find that your sigma real part is 0. Okay, so you get this, and your omega equal to 5. So another pole is negative, then you get another omega is negative 5. So with that, you can find the pole at sigma equal to 0, I omega equal to 5 and negative 5i. So for your 0, since x equal to 0, so when you compare to your sigma plus I omega, then you should know that 0 is at sigma equal to 0, omega equal to 0. So with that, we draw the 0 here. So this is the last example. So by using this formula, we know that ft equal to exponential negative 2t cos 5t can be converted to Laplace domain. You can find the pole where you let x plus 2 squared plus 5 squared equal to 0. Then you can get the pole at these 2 points. So for the 0, you can find it where you let x plus 2 equal to 0. Then you can get the 0 to be negative 2. And from the pole, when you compare x equal to negative 2 plus 5i with the sigma plus I omega, you found your sigma equal to negative 2, your omega equal to 5. And when you compare to the second pole, you found the omega equal to negative 5i. So this is the result. With that, you can plot your pole located at sigma equal to -2, at I omega equal to 5, and -5i. Lastly, for your 0, so your 0, when you compare to sigma plus I omega, -2 will be equal to your sigma when you compare the real part. So when you compare the imaginary part, omega equal to 0. So you can draw the 0